This is the last tutorial under the heading Calorimetry, and in this I'll be covering the last section, which deals with firstly changes of state, which is a concept I'm sure you all are familiar with, and more importantly latent heat, which again I'm sure you haven't done before. So there's solid, there's liquid, there's gas. This is something you've been doing since grade 3 literally. So when you have conversions between these three states, this is called change of state. There are names for each of these arrows. I'm not going to tell you all of them. I know that you know most of them. If you don't know any, you can go to Google, you can go to your book. I think that's a better source. So when you have these conversions, what you would have read so far is that these happen all at a specific temperature, like melting point, boiling point. So specific temperature, say it's T. Now if you have a solid, its melting point is T, you bring it to T and instantly it changes to a liquid. That's probably what you've been taught so far, but that is not very accurate. What happens is that it takes a lot more time than just an instant to convert from solid to liquid. Say you have the melting point at 0 degrees Celsius, you have a solid at -20. Now it's going to take a bit of heat energy here to get this solid from -20 to 0. Okay, you can calculate that using MC delta T easily. Now what you'll observe is that if you keep providing this energy for a while, the temperature is not going to change. It's going to remain at this 0 degrees Celsius. What you'll see is that the solid will start to convert to a liquid. It'll actually start melting very slowly. It's going to take time. That depends on its mass and other stuff, which I'll tell you about. But it's not that it just all converts at once. It's going to take some time, and you need to keep providing this energy over here. But what you'll see is that the temperature remains constant. Same, I'm denoting my temperature in blue. It remains constant, while in this area it's going down. I'm sorry, it's going up rather. Over here in this region, it's going up. Now, once this whole solid gets converted to a liquid, you'll have the substance in its liquid state, and you heat it up. Say its boiling point is 100 degrees Celsius. So from 0, you take it all the way to 100 degrees Celsius. This conversion is again going to take MC delta T energy in the form of heat. And again, you'll observe the same thing, that when it reaches 100, that water, or sorry, the liquid rather, is going to slowly start to expand and go to its vapor form, but the temperature is going to remain constant at 100 degrees Celsius. This is not going to change. So again, here you have to provide heat energy. That's a given. Heat energy is provided throughout this whole process. So to just draw the temperature arrows again. In this stage, you're increasing temperature, no doubt over here, but here it's remaining constant. So you can see that whenever you're changing state, your temperature remains constant. Now the reason I'm going to give you here, if you remember from the first tutorial, I told you that heat is all to do with the total energy, which includes kinetic energy and potential energy. Meanwhile, if you look at temperature, it's only to do with average internal kinetic energy of a body. It doesn't say anything about potential energy. Now, just to clarify again, kinetic energy is all to do with the motion of the molecules inside the body. Potential energy is all related to the distance between the molecules, the intermolecular spaces you would have said before. So more the potential energy, more will be the space between the molecules. Now, if you look at the graph again, I denoted heat energy in green. That's increasing throughout. There's no doubt over there. You're providing heat energy throughout. Now, your temperature, let's just take one particular section. Let's take this section over here where you're giving it heat energy. You're giving it heat energy, but you don't see a temperature change. You don't see a temperature change. That means that kinetic energy is constant. Kinetic energy remains constant. That means it remains constant here also. It's the same variable we're talking about. Therefore, and heat is increasing. So that could only mean one thing, and that the heat energy during this part over here is actually, it all goes to the potential energy of the body. It doesn't contribute to the kinetic energy. So this heat that you provide here is called latent heat. Latent. It's also called hidden heat. I'll tell you why. So as I said, potential energy is increasing, and potential energy is to do with the intermolecular space. So if potential energy increases, that means intermolecular space, I'm deciding it as IMS, also increases. Now you look at this. When a substance converts from solid to liquid, it is going to expand. You have few exceptions, but here we're just assuming that it expands. So you can see that this whole thing makes sense over here. During this region where the temperature remains constant but the heat energy is still being provided, your intermolecular space is being widened. So your molecules in the substance are going to go further apart. So the energy that you provide in the form of heat over here is going to go into increasing the space between the molecules, and so it's all going to go in the change of state, nothing to do with temperature. And the heat that you provide over here is called latent heat. Now usually you'd see that when you provide heat to a body, its temperature will also increase, but in this case, if you just look at the temperatures, naturally you'd say that uh, in this region here, you'd say that there's no heat energy being provided, but actually it is. So that's the reason why we call it hidden heat as well, and latent heat, because you can't really see it when you look at the graph. And just to draw the graph now, say you have I'm going to rub out a portion of this here. Say you have a graph that has on the x-axis it has time. So you've kept a body which is a solid at first. Say the body is at -10 first. This represents temperature here. It's degrees Celsius. And the x-axis represents time. So with increasing time, we're just drawing a graph with the temperature. Say you're providing a constant heat source to a solid at -10 degrees Celsius. What you're actually going to see is that after some time, it's going to come to zero. By the way, here we're assuming that we're taking this example here that the boiling point is 100 degrees Celsius, melting point is 0. So it's going to come to 0 first. For some time, it's going to stay constant. It's going to stay 0. The temperature will stay 0. You can see over here. After that time, when the whole solid has converted to liquid state, it's going to increase again. That heat energy will increase again. Say this is 100 over here. We're assuming that 100 is the boiling point. Again, it's going to stabilize for a little while. This is the time when liquid converts to gas. This here is the time when solid converts to liquid. This is when liquid rises, the temperature of the liquid rises. This is why the temperature of the solid rises. Sorry, it's a bit messy. And beyond this point, again, you're going to see that the temperature of the gas rises. So this is the concept of latent heat, the heat that you provide when this graph is constant in these areas is called the latent heat. And I'm out of time in this tutorial, but I'm going to make just one short one. where I'll definitely be finishing this off and maybe do a numerical as well